Welcome back, class. It's good to be with you again. In this next section, what I want to do is the confidence interval on correlation coefficient and the hypothesis test using correlation coefficient. So, key observation for the confidence interval, R is a number between -1 and 1. It's finite and bounded within an interval. So, in and of itself, its distribution is not ordinarily going to be normal. As such, it turns out that R.A. Fisher discovered if we do an appropriate transformation of the variable, we can make it approximately normal. Approximately normal here. Okay, so R, I'm just going to say, is not bell-shaped visibly, but Z, which is a function of R, is approximately bell-shaped. This is a horrible abuse of notation, but maybe that communicates something to you. So what is that transformation? Blah, there it is. It's a little funky looking. ln is natural log, and lo and behold, there we go. So its transformation is going to center at the true population center, and then it has a standard deviation that can be determined. Now take note, R is a statistic based upon other values. So this really is a standard deviation of the row. I put row, I meant Z. So it's a transformed value of row. So let's just put Z of row. Okay. Now, so we'll put that here as Z of row. So let's compute the confidence interval for our case of Deborah's exam score data. So Z now is just going to be 0.5 times the natural log of, and I'm going to put 1 plus 0.945. Hold all the decimal places in your calculator if you can. And I'm just going to put 3 for demonstration's sake. Now, that value is going to get us our Z, and we turn out to be 1.787. Okay, again, hold more places on your machine if you can do it. Standard deviation then is going to be the actual population value, which is 1 minus 5 minus 3, 0.7071. Okay, so when I come over here then, let's go ahead and enlarge the diagram so that on the bell-shaped axis, I actually have a 1.787, and then I'm going to add and subtract 2 times this guy right here. So 1.787 plus or minus, we use a more exact value, 1.96 times 0.7071, which is going to give us about 0.4 up through 3.17 is what this interval turns out to be. Okay, now if I want it on the scale of R, then the shape no longer matches. We do know the actual value, it's 0.954, but this 3.17 needs to be inverted to an upper bound on the correlation coefficient. The 0.4 needs to be inverted here. You can take this formula and solve it for R in terms of Z. That will give you the following result. R equals E to the 2Z minus 1 over E to the 2Z plus 1. Okay, so if I plug in for the first value, I'm going to have E to the 2 times 0.4, and then add 1 to that, over, subtract 1, and then e to the 2 times 0.4 plus 1, and that works out to be 0.381. And we're going to have r for the upper bound is e to the 2 times 3.17 minus 1 over e to the 2 times 3.17 plus 1. And that works out to 0.996. So when I come in then, I can put those numbers up, 0.381. On the R scale, this is my confidence interval, 0.38 to nearly 1. Pretty wide, but clearly something is going on there. So we're 95% confident the true unknown parameter is inside of that interval. And I can put my 95% on there. Okay, for the last part then, we want to look at a hypothesis test. Now, the hypothesis test is going to have a null hypothesis that rho, that is, the population correlation coefficient, is equal to 0. There's no relationship going on. The alternative then, you could do a 1 or a 2-tailed test. Typically, we think in terms of a 2-tail. Now, under the null hypothesis, if the data, that is x and y, are approximately normally distributed, then the following result obtains. R is approximately normal with the following standard error, and so if we scale R by subtracting it from the center, dividing by the standard error, it follows a student's t-distribution, just like the mean or difference of means that we've seen in chapter 11 and 12. Now, why didn't that work for the confidence interval? Because here we're specifying R is assumed to be 0. That is in the center of the curve. Without that assumption, it could be way out on the end. For example, taking a look at the other one here, look at this, it's 0.95. There's not a lot of room to go up on the right-hand side, so it's clearly very skewed to the left. In this situation, we are guaranteeing a symmetric distribution. Okay, that being the case then, R we've already computed from the other problem. That's 0.9454. 945, sorry. Okay, and the standard error is, let's see, 1 minus 0.945 squared over n minus 2. N is 5. We got that guy. 0.188. Okay, T3, that's going to be R minus 0 divided by the 0.188, which gives a 0.502. So we'll take 0.945 minus 0, that 0 comes from the null hypothesis, over the 0.188. That'll give me my t statistic, 5.02. That's going to tell me the p-value. Well, we can use R, or we can look up in the table. If we do look up in the table, then we're going to see that the probability that the T3 is over 5.02. It's going to fall between the 0.02 and 0.01. Here's the t-table, and we look at the two-tail alpha 0.02 to 0.01, 3 degrees of freedom, is here, 4.54 to 5.84. We got 5.02, which is in that region. We can also do that on R. Probability on the t-distribution, 5.02. Default is left tail, so I'm going to do 1 minus. And need the degrees of freedom, which is 3 in our case. So actually turned out to be 0.008. Now for the two-tail, we'll just double that. So 0.015 is the actual probability, which is indeed between 1 and 2%, as we noted. Okay, so using our work, we've got p-value is around 0.015, which is well below our usual benchmark of 5%. Therefore, we reject the null hypothesis. We conclude there is a positive correlation between our studied and exam score. Lastly, I'd like to do this on R. And so there's a function called core.test. And if I just put x and y in there, then I'm going to get the results. You'll notice that here's my correlation coefficient. Here's the p-value that I got before. And slight round off just due to that 0.02. And there's also the confidence interval, which we saw before. So we're all set. So that covers the basics of correlation coefficient with confidence interval and hypothesis test. We'll take a look at Spearman's rank correlation in class. See you then.